rework facility at a rate of 3 per hour. Okay, so there's our unit measure, hour, 3 per hour on average. The assembly line needs 4 ignition systems in the next hour. What is the probability that they will be available? And I'll further say to this, interpret that to be exactly 4 ignition systems in the next hour. Okay, not that there could be 5, 6, so forth like that. Just say that, interpret that to be the assembly line needs exactly 4 ignition systems in the next hour. What is the probability that they will be available? Okay, so back to I kind of hammered that point about, be careful to read what your units are in terms of whatever rate you're provided. So here's an extension of that. If events in a Poisson process occur at a mean rate of lambda, which is always positive, per unit, per hour, per week, per specified 100 feet of whatever coil or screen, whatever those other examples were, then the expected number of occurrences in an interval of length t is lambda times t. So if I were to say mean rate of 2 per hour, and I tell you that the shift is 8 hours long, then for a shift, if I say, well, what's the expected number of occurrences in a shift, it's simply going to be 2, because you had 2 per hour, times 8 hours in the shift. 2 times 8 is 16. We'll see some examples of this in a moment. Could be, if I say there's a number of flaws, there's 5 flaws per 100 feet of whatever wire, and I ask you for 1,000. What's the expected number of occurrences per 1,000? So that's just going to be a factor of 10. 10 times 5, 50. So that's what you're talking about here, is saying, well, we'll take it per unit and then extend it over a larger interval. The number of occurrences, say x, in the interval of t has a probability distribution function. Again, that should be a capital X there. What's the probability that x, your random variable x, is equal to k? And that's for the bigger interval, okay? Is equal to, that also, it's a Poisson distribution, but now the expected value for that distribution is lambda times t, so probability that x is equal to k, some number of faults, some number of calls, some number of occurrences of an event, is equal to e to the minus lambda times t, times lambda t to the kth power divided by k factorial. All right, and the mean of this distribution is lambda times t. The variance of that distribution is also lambda times t. So again, that's where working with a Poisson distribution, you want to make sure of what is your rate given in terms of what unit is it looking at. Telephone calls enter a switchboard on average of every 3 minutes. If one assumes an approximate Poisson process, what is the probability of 5 or more calls in a 9-minute period? So see the flip between every 3 minutes is what you have your rate data associated with, and the question being posed is what's the probability of 5 or more calls in a 9-minute period. 9 minutes, of course, is a 3 T then, in that case, is 3. 3 times 3 minute intervals if the unit measure is 3 minutes. So the mean of your Poisson distribution then for 9 minutes is just going to be 6. 2 calls every 3 minutes, so therefore 2 times 3 intervals, each of 3 minutes long. 6 calls per 9 minutes is the average. And then you can go and you can verify with this is both your mean and your variance. You can fill that into the previous formula provided. So you would have e to the minus 6 times 6 to the kth power divided by k factorial for probability of more than 5 calls. And this came out of the table. So probability of 5 or more would be the same thing as the probability 1 minus the probability of 4 or less. And so you get 0.715 as your probability. Okay, I've got a textbook exercise for you to work on associated with this. And again, if you'll work through these, and then we'll do some more when we meet up in class. And this concludes this recording session.